Okay, welcome to the 8th common session of Sunoikisis's Digital Classics 2017. Today we have a session about computational morphology, and we have two guests, Doug Haug from the University of Oslo and Barbara McGillivray from the Alan Turing Institute. Doug was with us last year, but also a few weeks ago, because he taught already a session about tree banking, the first session about querying tree banks. And Doug was with us also in December in Leipzig for the planning seminar of Sunoikisis's Digital Classics. So he helped us to build the syllabus for this semester. And Sunoikisis now is also an official course at the University of Oslo, so we are very happy about that. Barbara is a new guest. So Barbara, welcome to Sunoikisis's Digital Classics. We are very happy to have you in our community, so thanks for joining us and for contributing to this program this year. So as I said, this session is about computational morphology. This is an introduction to computational morphology for Latin, and this is an introduction to part-of-speech tagging and tagging of other morphological features using existing tools for Latin. You have the class outline in GitHub, with the description of the class, with readings, and also a practical exercise. But I think that now we can start, and Barbara is starting. So welcome, Barbara. You can unmute yourself. Okay, excellent.
Hello? Can you hear me?
Yes, it works.
Thank you, Monica. I'm very happy to give this first lecture. So I'm going to share my screen. Can you all see my screen?
Yes, it works. We can see the slides.
So I will take care of the first part of this lecture, which will be introducing some concepts of computational morphology. So it will be a bit more theoretical, and then Doug will be with you in the second part, giving you more practical instructions and show you how to use these concepts in practice. So I'll start by saying what is computational linguistics and computational morphology. If you're wondering about that, one definition of computational linguistics is well, a very highly interdisciplinary field that aims at teaching computers how to process natural language. So this is a field that originated in the middle of last century, and it progressed with the advances of computer technology. And the idea is that we can analyze language in automatic ways if we teach the computers how to do it. And by doing that, we can have humans focus on the most challenging and creative tasks and leaving the computationally intensive tasks to computers. But this is actually not just a one-directional relationship. We can also benefit and learn more about how the language works by trying to model it computationally. So there are benefits for theoretical linguistics as well in developing computational models. You might have heard of computational linguistics or other related terms. For example, natural language processing is broadly speaking a synonym of computational linguistics, and it's very popular in fields like data science, machine learning, and it focuses more on the applied aspects of computational linguistics. In a similar way, language technology, which is, again, broadly speaking, a synonym, but it's more focused on the technological aspects of computational linguistics. Language engineering as well is the applied side of this field. So if you think you haven't interacted with computational linguistics before, you're probably wrong, because nowadays there's a number of ways where we can interact with applications of computational linguistics. For example, if you've used a virtual assistant like Siri or similar on your phone, then you will have experienced interacting with the dialogue system. So dialogue systems take spoken input, and this is through a series of steps. They then produce a spoken output. So the person speaking to the dialogue system will have formulated, for example, a question, and the system will have to convert the spoken input into some kind of transcription. It will then have to analyze this question, for example, to identify what is required, and then it will have to match it to some source of knowledge. For example, if I'm asking who is the president of the United States, the system will have to identify that I'm looking for an answer like the president of the United States is, etc. And then the system will have to formulate the sentence in natural language and then convert it back into spoken output. So it's quite a long process, and it involves a series of steps, but they're all related to computational linguistics. Another example is machine translation. If you've tried translating things on Google Translate, well, you may not be too happy about the translation, but in fact, if you think that it's a machine doing it, it's a very, very hard task. It doesn't do quite that bad. And machine translation systems rely on lots and lots of texts that are parallel. So they have a version in one language and the corresponding version in another language, and then the computer will learn the mapping of the two languages by learning the pattern corresponding in the two languages, and it's improving all the time. So it's a very promising field. Another application is information retrieval. So whenever you do a Google search, you will have interacted with a number of computational linguistics tools. So for example, if you search for cook on Google, or maybe even cooks, then Google knows that this could be the plural of cook, or even the third person singular of the verb to cook, and it will present you with a list of web pages that are relevant to your search. It might even show you the Wikipedia entry for Thomas Cook, the explorer. So if you give it a bit more context, it's likely that it will be able to understand if you're looking for cooks, people who cook, or actually the historical character. So again, there's a lot of processing behind these information retrieval systems that allow intelligent, smart interaction with a human user. Another couple of examples: spelling correction. So if you've seen that in word processing software like Word, Microsoft Word, then you will have noticed that if you misspell a word, you usually get a suggestion for correction, and that relies on a combination of dictionary data and systems that are able to identify misspellings in context. So that's again an application of automatic linguistic processing. And finally, computational lexicography is another area where we have applications of computational linguistics. I myself have worked for the Oxford Dictionaries, and I've seen how computational linguistics and lexicography really work together today to make dictionaries. So, for example, if you search for ate in the Oxford Dictionaries, you'll get suggestions for the entry for the verb to eat. So there is some morphological processing going on to analyze the search term and map it to the dictionary form. So this is all good, but it sounds like it's a field meant for modern languages. But we're here to talk about ancient languages. So what about them? Well, it turns out that ancient languages, and in particular Latin, played a very important role at the very beginning of the field, computational linguistics. Back in the middle of the 20th century, Father Roberto Busa got a lot of funding from IBM to create a huge corpus of Thomas Aquinas texts. And this project went on for several decades. You can see Roberto Busa being quite young on the left hand side, and then he was a bit much older when the project was finished. And this project followed the technological evolution. So it's now the Index Domesticus is now available in digital format, and it's actually partially been syntactically annotated. So as I said, Latin was the language of the Index Domesticus, which is the first electronic corpus. And then what happened is that the focus went on modern languages for obvious reasons, because languages like English have clear commercial applications. But in the past decades, there's been quite a lot of research efforts put into classical languages from a computational point of view. And I won't go into any detail, but you can have a look at my book that summarizes the state of the art in Latin computational linguistics, particularly. And I've made the introduction chapter available for this lecture with permission from Bill. And it also shows some new research results. It's true that for ancient languages, there aren't not as many clearly commercial applications for computational linguistics research, but there are certainly educational and academic applications. I mentioned lexicography, which is a field that I'm familiar with my experience at the Oxford Dictionaries, and it's definitely very important to be able to use computational linguistics in the making and updating of dictionary entries, because dictionaries need to be updated, even if the ones for dead languages, as we acquire new texts and as we want to add more levels of analysis, we need to keep the resource under active control. And then stylistics is another clear application of computational linguistics when we want to analyze, for example, the linguistic features of an author. We want to be able to mine their texts at a large scale, and instead of having to read or manually analyze the text one by one, we can rely on automatic means. Linguistics obviously is a field that benefits from computational methods, because we can learn about how the language works by developing these tools. And of course, any other field that relies on historical text can benefit from computational linguistics. So if we want to study any change of concept over time, for example, we want to analyze the text, and having access to automatic ways to analyze the text is really important. Philology, of course, has its own computational field, computational philology, that has made philology move further thanks to computational methods, and other fields as well. So just to give an idea of why this is relevant, even for classical languages, not just for modern languages. So this lecture is about computational morphology, which is a subfield of computational linguistics, dedicated specifically to morphological processing of natural language. Yes, natural language. And it's a level of analysis that is the basis for further processing. So if we want to do syntactic analysis or semantic analysis, then we need to have the morphological analysis in place, especially for morphologically rich languages like Latin and ancient Greek, where knowing the morphology helps us towards understanding the syntax. It's a step that is towards the beginning of the pipeline, if you want to say, but it's as I said, really, really important. And I hinted at annotation, corpus annotation. I'll say a few more words about that now. So this is an overview of the pipeline. So the first step in processing language consists in finding the words, identifying the tokens. So that's the first step. And then we have the morphological steps, which we can divide into three: lemmatization, morphological tagging, and part-speech tagging. These go together, as I'll explain later, and they kind of support each other, and they form the basis for syntactic parsing. I mean, this is not a strict order. You can skip some steps, but logically, these are all steps that build on each other. And then once you have the parsing in place, or if you want to call it syntactic annotation, then you can go on to more deeper levels of analysis, like semantic analysis. So if you once you know which words are the nouns and the verbs and which ones are subjects and objects, and then you can go on to looking at the meaning of the words in context, for example, finding synonyms of words, or finding the role played by the different entities in the sentence, for example, the patients, the agents, the actions, and so on. And then you can go even further into named entity recognition, relation extraction, keyword extraction, topic modeling, so trying to find larger items of interest in the text. So these are the building blocks that, as I said, are not presented in a strictly linear order, but it's helpful to imagine these steps one after the other to understand how they build on each other. There are different ways of annotating texts, as you will have experienced. Manual annotation is, of course, the method that you've heard about when learning about tree banks. In this lecture, we'll focus on the automatic approach to annotation. That's when we develop algorithms, or we use existing algorithms to annotate corpus. A compromise between these two is the semi-automatic annotation, where normally you'd apply an automatic method, and then you would manually correct the results by hand. And then another way to perform annotation is by relying on large number of annotators, so-called crowdsourcing, even though the number of people were able to perform the annotation in your ancient language may not be exactly crowd, but the concept refers to a large number of people that work together on this task, and then you'll have mechanisms for controlling the quality of their annotation and their consistency and their level of agreement. But we'll focus on automatic approaches, and there are two main ways of performing an automatic annotation. the first one is also the first one from a historical point of view. It's a rule-based annotation. So that's basically, that consists in having a list of rules that specify how to annotate different linguistic phenomena. So, for example, if you want to decide how to say whether a word is a noun or a verb, you may say that it has a certain ending, it's more likely to be a noun, etc. And then you can have rules for specifying very specific, say, phenomena. But that's the approach that was used at the beginning of the field, and it's now been outperformed by a second type of approach, the so-called statistical annotation, which relies on machine learning. So the idea here is that instead of telling the computer a series of rules to apply, we give the computer a large amount of training data. So this is text that we have annotated by hand normally. So the computer will then have the text and the annotation, and with enough data, it will be able to learn the patterns that tend to occur. So, for example, if we've given the computer text with part of speech tags, so labels such as noun and adjective and preposition and verb, etc., then the computer would learn that certain words can only be nouns, other words can be both nouns and verbs, for example, and certain sequences of labels are more frequent than others. So, for example, noun, verb, noun in English is much more frequent than verb, verb, verb. So it will, with enough data, it will be able to learn these rules by itself. And when we then give it new data, it will be able to assign the labels itself. And what we can do is provide it with some data that we know what it should look like, and we can see, we can compare the annotation from the system with the annotation that we know is correct, and we can assess the performance and then improve the whole process. So it sounds very high-tech, and it can be, but it's really the most effective way to perform annotation. Some challenges, of course, because it needs a lot of annotated data. So you have to invest in producing the annotated data, and that's why projects that build tree banks are particularly important, also for computational linguists. So to talk about automatic morphological annotation. So as I said, morphological annotation covers the three steps: that lemmatization, which assigns the dictionary entry to a form; morphological tags, so labels like case, number, gender for nouns, or person, mood, tense, etc. for verbs; and the part of speech tags, which can be as basic as noun, verb, preposition, etc., or can be a bit more specific depending on our choice, really. So this is just an example of some Latin words with their morphological annotation, and you can see that depending on the part of speech, we have different morphological tags, and also the same word may have different analysis depending on the context, and I'll go back to this later. But if you're a linguist, you will be convinced that this is really important, and morphological annotation is absolutely essential. If you're not a linguist, you may wonder why bother at all. And so it just may be worth pointing out a couple of reasons why this is important. What you're interested in is not necessarily the linguistic analysis per se, but extracting information from the text, then morphological annotation allows for a deeper level of analysis of retrieval of information. So, for example, if you're a historian interested in terms around friendship in a certain time period, and you have a set of texts, you may want to search all instances of synonyms of friend, so amicus, sortus, etc., in the text. But you may not want to specify all the possible inflections of these words in Latin, because that's a lot of work, and it's not really a scalable approach. You don't want to have to specify all the case inflections and etc. For all the words you're interested in. So then having access to a morphological annotation tool will allow you to just specify a list of lemmas and be able to retrieve all the inflectional forms. So if I say amicus, then I'll also get all the accusatives and the datives and plural forms, singular forms, etc., etc. Also, of course, having morphological annotation means that we are a step further towards a more advanced type of linguistic processing. So say I want to look at synonyms of amicus, then I may do some fancier semantic analysis. But if I don't have the morphological analysis in place, then I cannot go very far. And why automatic morphological annotation instead of manual morphological annotation? Well, there's a number of reasons that really shared among automatic approaches in general. It's not specific to morphological annotation, but it's the idea that if you have a system that does it for you automatically, you can scale up the system. So say that you want to analyze 10 texts, and you can do it by hand. But if your texts suddenly are 10,000, then you would need many, many, many more people to annotate all those texts. Whereas if you have an automatic system to do it, trained on manually annotated text, of course, high quality text, then you can run the annotation on larger sets. I mean, it's all about having the right level of confidence on the quality of the annotation. That's the really tricky aspect. But conceptually, once you have a tool that performs well, then it is scalable. Also, the type of errors that automatic annotation tools make tend to be consistent. So humans make mistakes, machines make mistakes if they're not programmed well, but the type of mistakes that machines make are usually very, very consistent. So we can tackle them directly, and we can try and fix them. Whereas when a human makes a mistake, it's often really, really difficult to identify. And of course, from a cost point of view, once you've set up an automatic annotation system, then after the initial costs of running it, then you can run it on larger sets of text at much, much smaller cost than if you were to do it manually. Of course, there are questions around data storage and computational power, but it is still a much more scalable approach, provided that you have good starting manually annotated data to start with, at least. So, okay, it sounds like a very, very basic and important step, but maybe it sounds very trivial. So why is not that trivial? Well, it depends on the language. But for languages with rich morphology, we have a very high inflectional variability. So a noun in Latin can have, or even a verb, say, dozens of different forms. And that means that the system, a machine learning system that sees all these forms, will perform better at analyzing unseen forms if it has seen enough variability. So for rich morphology languages, then we need a lot of data to expose the system to as much variability as possible. And if we don't have much data, we have problems technically called data sparseness problems. So that's one challenge. That's why large training sets like tree banks are really important. The other challenge is a disambiguation context. So the morphological analysis of a word is not necessarily the same in any context. Just an example, if we have rosam in Latin, it could be the singular accusative of the noun rosa or the participle of the verb rodo, to gnaw. So unless we're given a bit more context, we cannot really tell. And same challenge goes for a computer trying to analyze this form. So that's why it's not enough to just specify a list of words and their analysis to be able to teach the computer how to do it. It's important that the computer understands the context. And how to go about doing this, at least for Latin? Well, there are some tools available. I've just listed a couple, but there are more for doing morphological analysis. What we'll talk about here today is how to use one tool that relies on machine learning. It's the tree tagger algorithm that Doug will talk about in a second. And this is an example of a machine learning tool that relies on kind of statistical approach. And as I said, generally speaking, machine learning tools for Latin rely on existing tree banks. As I'm sure you're familiar with the three main tree banks: ProYo project in Oslo, Latin Dependency Tree Bank at Persis, and the IndexNet Tree Bank. So I am done, and I'm ready to hand over to Doug for the second part.
Okay, thank you, Barbara. Now is Doug. Okay, good.
Okay. Hi, everyone. And thank you, Barbara, for giving us a nice introduction surrounding these tools that we're going to look at. And in particular, as Barbara said, I'm going to show you one tool that we can use for morphological tagging of Latin, and that's the tree tagger. I'm going to share my screen. So let's see, we can do this. Right, okay, and I'm going to go this thing here so I get recursion. But here, okay, so the tool we're looking at mainly today is tree tagger, or speech tagger for many languages. The advantage of tree tagger is that it has some pre-trained models for Latin, as you can see here, or Latin parameter files. So because tree tagger itself is an algorithm that learns from data, right? It learns what likely morphological analysis of words are. So the normal way to use a statistical tagger will often be to devise your own training corpus based on tree bank data, and then to train the tagger on that corpus, and then use the result is called a model, and then the tagger can use that model to tag unseen text. So most of the time today, we're going to use pre-trained models. So that's an advantage. So you don't have to bother about the training step. But if we have the time, we may look a little bit on how to also to train the tagger. Tagger lives on this website. This is where you can get it. It's distributed under an open license, and you can download it from here. We are going to use the Windows version you can see here, which also includes a graphical interface. So now I'm going to show you this part of the lecture will be very practical. I'm going to show you how to download things, to arrange them properly so that you can run it. Yeah, do all of that. So now I'm just going to save this file with the Windows version of the tree tagger. And I'm going to also the Windows interface. Right, so I clicked on a link that is available from the tree tagger site, and here we get an interface. You need 3 files here. Well, at least for the first one, we only need actually 2, the tagger program and a text file that it needs. There's also a Windows interface to the training program. I don't know if we'll have the time to look at that. So we'll see. So I'm going to download that as well. So here and here, and now we have all the relevant files. So you can see here what I have a zip file containing the Windows installer, and then I have the file called TT models and the executable that contains the graphical user interface. So first, I'm going to unzip this. So now we get the tree tagger directory. We're going to move this text file into the tree tagger directory and the executable as well. Again in here, and now we're going to put the TT models in the lib directory and the executable in the bin binary directory. So now we have a working installation, basically. So we can have a short look. Inside the bin, there will be various bat files that you don't need to use. And then there are the executables, which are used for tagging and for training. And then the graphical user interface. These executables will read models that have been trained from the lib directory. So there are various models involving well, first of all, there are files that tells the computer how to expand abbreviations whenever they occur, and then this is where we can put morphological models once we've trained them or once we just downloaded them from the web page. So next step is to download such a model. So now we go to the tree tagger page again, and I'm going to use the Latin parameter file. You'll see there are 2. So there's one Latin parameter file, which was compiled by Gabriele Brandolini from various resources. And the various resources you can see means the Proyal corpus, the Perseus project, and the Index Thomisticus. So the Proyal corpus at this time contained the Peregrinatio Aeterea and Jerome's Vulgate, so not really classical Latin. So a problem with this model we'll see is that it contains a lot of late Latin material, and then the only classical texts are the one from the Latin Dependency Tree Bank, which is quite small. And this is the one we're going to start with. So when we download this, yeah, I'm just going to mention that there is this other Latin parameter file that we'll look at afterwards, which has been trained on the Index Thomisticus tree bank. So that's only Thomas of Aquinas material. So if you use that to tag classical text, it will likely perform worse. So now we download this parameter file. I'm going to save it in the tree tagger lib directory. And now I open the folder. It's a gzipped file, so we need to unpack it. And this gives us the model Latin par. Okay. Now is the time to look at the file TT models. TT models.txt is a file that defines the models for the various languages. So here you can see that the English model lives in a file called english.utf8.par or just english.par, and these differ in encoding, right? So you see for Latin, it says that the file is called latin.par, and the encoding is unknown, but we're basically going to use Unicode text here. So I'm going to type that Latin text will be in UTF-8. OK. So now the tagger has everything it needs to know in order to tag text. So the next step is to find a text that we can tag, right? In principle, the tagger wants a file that contains every word on separate lines, right? So we have performed what Barbara briefly talked about, which is called tokenization. That is splitting up the text into tokens, words, right? But if we don't have that, the next best thing is to have a pure text file containing some Latin text and no formatting at all. And then TreeTagger will automatically tokenize that based on its own tokenizer. So I'm going to just briefly this is documented. Oh, let's see, sorry, that is the documentation is here, I think. So okay, well, it wasn't. Let me see if I can find it. If I can't find it, so really, the built-in tokenizer of TreeTagger does nothing very fancy. It splits the text whenever there's some white space. So that's all it does. And this gives, because of the writing system of Latin, this gives reasonably good results. But of course, what we're not going to get from the default tokenizer is splitting off, let's say, enclitique, arma virumque, right? It's going to treat virumque as one word because there's no space. So in order to improve performance, eventually you'd want to have to run a proper tokenizer first. Yeah. Okay. So, but we're just going to work with text that we can download. I decided we could as well use the beginning of the first speech line. So that here from the Perseus project. Now we can take this text, we copy it, we go to this directory. Maybe we're going to put this in a different directory. Maybe we're just going to put it here. I'm going to create a new text file. Line. I'm going to open this text. Oh, I'm going to open it. I'm going to use something called Notepad++, which lets us do some easy editing of the text. So that's here. And now I just paste in this thing. Okay, it shows us one single line. There are no line breaks, but I can just tell it to write this thing. Okay. Now, if you look at this text, it's almost without formatting, but there are some annoying numbers, right, which correspond to these, the footnotes in the Perseus text and the paragraph numbering, etc. So we want to get rid of that before we start tagging. So this gives us a nice opportunity to practice regular expressions, as we discussed a couple of lectures ago. So I'm going to show you how you could deal with that. Obviously, we're now looking at a very short text, and the easiest way to remove numbers would be to just delete them by hand. But if you had a longer text, that would be tedious. So I'm going to show you how you could do it in that case. So let's go here, search, in this case, replace, and this editor and many other editors you can find on the market will contain a find and replace mechanism that can use regular expressions. So now what do we want to get rid of? Well, if you remember from regular expressions, we're going to delete notes, and they're defined by this character class called \d. There may be one number, there can be several in a row, so that's d+. And then also we see in this text that we have things like square brackets, that we want to eliminate. So I'm going to take away those as well. I'm going to say square brackets. There's a backslash here because we need to escape this. If you don't remember the details, you should go back to the lecture on regular expressions. So I put a question mark after that means 0 or 1, left bracket. And then after the number, there can be, in some cases, a dot, and in other cases, a closing bracket. So now I'm going to define a new character class containing dots and right brackets, which again need to be escaped, and then question mark. So now let's just try this out. So find next. Okay, finds this, and I replace it. Okay, now it finds the next. I replace it. Replace it. So here it will match the brackets as well. So I can replace it. And if you're working on a big text, it will be a good idea to do this a number of times and to see that it actually does what you want it to do in the different cases. And then once you're done with that, you just click replace all. So that was a little practicing of regular expressions again. And now we have a text that is pure in the sense that it's a text file containing only the Latin text that we want to parse. So next step is not to parse, but to tag. So we often say we tag when we do morphological analysis and we parse when we do syntactic analysis. So now we want to tag this text, and we run tree tagger. So the tree tagger we put in this directory, and the executable is in bin here. And since we're working on Windows, we have this nice graphical user interface here. So this is safe. The publisher could not be verified. This is academic software, so there's no real publisher in that sense, but this is safe. So I'm just going to run it. And here you see the interface to the tree tagger. It knows only one language, Latin, because that's the only language we told it about, right? So remember, when we worked on the models file, there are various defined, but the only file that actually exists now in the lib directory is this latin.par. So you cannot find any of these other files, only latin.par. So that's why the only language it knows at this stage is Latin. Okay. So the easiest way of using it is just to provide an input file, right? I click on input file. So now I choose Cataline, and then an output file, and I can call it whatever I want. Let me call it Cataline. Okay, and we run it. So it will be assumed to be UTF-8. That's okay. And there's no abbreviations file defined for Latin, so it won't really know what to do with the Titus and Quintus and all those abbreviations. But let's look at the other stuff. So I get this, reading parameters, tagging, and finish, and I continue. And it's finished. So now, if we go to this directory, up here we have not just the original Cataline.txt, but a new tag file. And here it is. So let's see. Let's have a look at the output. So the tokenizer put the words on different lines, right? So that's the first step that was done. And then it provides, so it gives us what's called a tab separated file. So the first column on each line is the form in question, the word in question, then there's a tab character, and then there's a tag, and then there's a character, and then there's a lemma, right? So what it thinks is the correct lemma. So as you can see, these tags in the pre-trained model are not very detailed, but they still give us something to work with. So for quo, for example, it thinks this is a rel. Look at the documentation. So let's go here again. So if to the file where we downloaded the parameter file from, the page where we downloaded the parameter file from, here you see there's a text at documentation. So these are the tags. Oh, did that? No, that was not the our tags. That was the Italian tags. So this, right. So the Latin tag set is, on the other hand, documented in Italian. But okay. So you see, rel is the tag used for relative pronouns, but it doesn't give us any more information. It doesn't try to disambiguate case or anything, right? So the only thing we get for a relative pronoun is rel. But we got that, and obviously that's not really what we wanted here, because this is interrogative. Let me just say what it wants to. So does it? So I guess we would have wanted just pron, since rel seems to be relative pronouns, but that's an obvious case where it's hard for the program to tell. So let's just look down a little bit. We get lemmatization, which in many cases is correct, right? So it does see that abutere is a verb and it's indicative and it belongs to abutor, right? So this it gets right. And generally, if you look at this, we can't spend too much time looking at this file now, but generally the quality is decent here. So it makes some obvious errors, right? Like it doesn't recognize that patientia here is an ablative depending on abutere, so it thinks it is a nominative, probably because that's a much more frequent thing. But it does recognize, for example, that Catalina is a vocative. And this is because these taggers, what they use in order to disambiguate whenever they have several options, is they look for the context. And in this case, because Catalina is set off by punctuation, it's going to guess, oh, this is probably a vocative. Okay, this is the easiest way of running a tree tagger, and in many cases, this will give you good enough results. But we can run it in different ways. So I'm just going to show you that. So let's go back here. We can, for example, tell it to give us all tags that are, here it says up to half time as probable as the best tag. So let's do that. Now I'm just gonna put, oh, sorry. I'm gonna call this cat line. We get probabilities, and now we run it. And we have a new file here containing probabilities. Well, containing, sorry, the alternative tags, right? So now we can see, if we look at the beginning here, we can see that it thinks nominative, patientia, or yeah, so it's patientia is either the nominative of noun patientia or it's the ablative of noun patientia. We can also tell it to not just give us all tags with a certain probability, but actually give us the probabilities. So let me run it again. So, and now we can. We need to reopen this file. So then we get something like this, right? So we can see that it thinks patientia is a nominative. I think that it gives that tag 61.8% probability, and the alternative tag ablative gets 37% probability, and then there's probably a tiny little probability for a vocative, which is why these numbers don't add up to 1. So that is what it looks like. You can see that in many cases, it will not be able to give you a lemma. In particular, this can happen whenever the tokenization went wrong. So here, for example, nihil ne. This obviously is not really a word. This is nihil plus the question particle ne, but somehow it thinks this is a vocative, nihil ne, and it's just not smart enough to think that this, if it's a vocative, it must be the vocative of nihil nos, which doesn't exist, obviously, so it might as well. Okay, so this is the result we're getting here. I can briefly show you what happens if we, well, if we look at the available tags here, tag sets here, we could also download the other one, right? This other one, the Latin parameter file, based on the index Thomisticus, is much more, it contains a much more detailed tag set. So it would be possible to use that, but it often actually goes even more wrong because it's based only on Thomas's Latin. So what I wanted to show you briefly now towards the end is how we could train a better model ourselves. So for that, we will need training data. And that is complicated. But in this case, we're going to use something from a project called Universal Dependencies. Universal Dependencies contains versions of the different Latin tree banks. So here you can see the Latin tree bank. So the biggest one is the index Thomisticus tree bank, but it's only late Latin. The Persis tree bank is quite small at 18,000 tokens, and the Braille tree bank has 160,000 tokens. So we're going to use that one. You can download the Universal Dependencies corpora from here, and what this would give you is this. The corpus has been split in several files, and for example, there is a training file. That will be the one to use. It looks like this. Contains columns with a number for each word, the form, the lemma, the part of speech tag, and the another way of stating the part of speech tag, and then the morphological analysis, and then some syntax over here that we're not going to look at. So this would be the training corpus, but tree tagger and other taggers in general want, again, a format where you only have the form and then followed by the tag. So we could pick that and that, for example, to build the tags. Again, if you've been doing regular expressions, that should do it. So I'm going to show you that very briefly. Let's have a look, find. So that's why learning regular expressions is really a good thing. So definitely something you should do. We now want to define a character class containing everything except tab characters and new lines. So we get some of that stuff, and then we get a tab character because that's the way it's structured, right? So this, you can see, find each column, as it were, and then this pattern repeats. So we're going to say have get, and then at the end we may want to say we're going to get the rest of the line. So now we get lines, and we can actually say that in the output we want to have the second column. If you remember this, do this. The second, that'll be here. Put these in the output. We can refer to them in this way. I find this, and and we want the new line character here, and I replace, and I replace, and so on, and I get all the tags. So be the way of doing things, of creating something that could serve as a training file for tree tagger. But this file is big, and it will take a long time to do it. So I cheated, and I actually have some training files pre-created. And I'm going to train a lot with that now, and then we'll look at that finally as the last thing we do. So to train a model, we need also to download the final part, which we did not get. So sorry, that was here. The Windows interface to the training program. So now I'm downloading that as well. And let's see. Got it here. We need to put it in the tree tagger directory. Here. And then we can train a model. It wants a number of files that I'll give it, which is these training files. So let me see, that will be here. Yes, so it wants a lexicon file. That's here. It wants a file defining the open class items, the ones that can be used for any word. And it wants this tag training file, which was created the way we just looked at. So that will be doctor text. And then we wanted to output a parameter, and we might as well tell it to put this where we want it in the tree tagger directory, in the lib directory. And we'll call this Latin proel because it's on the proel. Now I run the trainer, and we're done, and we now have a new model. So if we get here, we now have in the lib directory, we have this Latin proel par. We need to tell it that it can use this. So now we're going to define another language, which we call Latin proel. And so, and we save this. Oh, and they won't actually close that, and then we can save this. So now I'm going to reopen, tree tagger here. I'm going to tag, we're going to run it. Oops, did I? This I don't want. Complaints about a small typo in this directory, in this one. Let's see if that was okay. Okay, let me see. So now we find it again here. Yeah, so now we have a new language called Latin proel. We can tag with this. And now we're gonna use again the Catalan text, and we're gonna create a new output file called Catalan. So we're finished, and we open the file to look at it. Oops, it goes here. So here, yeah, we get more detailed tags. It still thinks quo is a relative pronoun, but it correctly identifies it as, well, quo. It's really not so in this case, the analysis. Correct analysis here. So, for example, it does know that paciente is an ablative feminine singular, does know that this agrees, and we get pretty detailed tags that we can then use for our own research. Although we need to carefully analyze the file and see what kind of errors it makes, because that's the snag with all this statistical tagging. It's never going to be anywhere near 100% correct, so we do need to be careful in using the data. So now let me turn off my screen share. Does this, no, it doesn't. How can I do that? Ah, okay. So, and I'll move this over to the camera. Otherwise. So that was it, I guess. And we're ready to take questions.
Okay, Doug, thank you very much for this practical thing. So thank you both for the introduction, and this is what we need in Sunoikisis. So both slides for presenting, introducing things, and then practical exercises. So questions, please. We have a big audience today.
I have a very simple question. Is there any training data for ancient Greek that one could use?
Yes, there is a lot, actually. Again, the best place to go, I think, is the universal dependencies page. Let me show you that. So I'm going to share my screen again. Let me see. So it doesn't. Here. Okay, let me share my screen again. So if you're working on ancient Greek, the place to go is the universal dependencies corpus, because the universal dependencies project is a project unifying various resources. So you'll see that there are two corpora here. The ancient Greek is the Persis corpus, and ancient Greek Proel is our corpus. And these two corpora have not yet been completely unified. That's why we maintain them as two different entities. But in terms of morphology, the analysis is in principle the same. So if you combine these two corpora, that will give you 400,000 tokens of training data, which should give you really good results. That's really more than enough to train a decent morphological tagger.
Great, thank you.
Started. Oh, here we go. Yep.
Okay, other questions? Well, of course, I think so. We mentioned training data. So this is a common topic for our common sessions. Also, last week we had a session about prosopography, which is a very different topic. But again, how do we collect data? So that's the big question. We have data, we have seen, but we need more data. And we need the manual work, as we have seen. But of course, we can't think of tagging everything. So that's the thing. So this is a basic question, especially for those who don't know this field. So how do we produce this data? So how can we optimize this? So yes. I know this is a big question.
Yeah, that is a big question. I think we're now at the stage where we have enough training data that we can really bootstrap good morphological taggers, and we can use that as input for morphological disambiguation, right? So, and this is what I believe they're doing in the ancient Greek dependency tree bank, and this is definitely what we do in the Proel project. We no longer tag text completely from the bottom manually. We train models like this with tree tagger or other statistical taggers, and then we get very good results. As you saw, we can also get with the probabilities, right? So we can ask annotators, for example, to look at anything the tagger was a bit unsure about, right? So maybe there was some alternatives that were almost as plausible, and then the annotator can see that and then make a choice, right? Whereas in other cases, the tagger will be so sure that we may perhaps say that this is good enough and no human needs to look at it. And in that way, I think we can get further even faster now. And once we have a bigger corpus, right? So if we do that and we double the size of the corpus to 1 million tokens, we can train afterwards an even better morphological tagger, and so it goes. So this should really be a priority going forward, I think, yeah.
Yeah, I think this is important to understand. So this is a sort of step-by-step workflow, in the sense that, of course, at the beginning we started with manual annotation, then we generate a first set of data, then the machine works on this data, then we get results, and then we can start disambiguating and so on. So okay, this is a very simple way to, to explain things, but basically I think this is the method, not only for part-of-speech tagging, but also for other things we need to disambiguate. We saw that last week with name entities, and also next week we have a common session about name entities. So this is again the problem, and then in that case, of course, we have another problem, because for example, with Morpheus, the work is based on dictionaries. We don't have many name entities in dictionaries, and so that's why we need more data. And then we need to disambiguate them to get inflected forms and so on. So I think this is important.
Yeah.
Okay. Other questions? Other things? So we still have a few minutes. Well, it was very dense, but I think very clear. So really, now we have the tools. So our audience our students, they can experiment with these tools. And of course, we need more data. So please annotate, please.
Yeah.
Yes. Yeah. Other questions we have? Yeah, please. Gabriel, you wanted to say something? Ah, sorry.
Sure. No, can I just ask a follow-up question then to my question? Doug, you mentioned about merging the Perseus and the Proel tree banks to make a bigger chunk of training data. Is that as simple as just running both of them as training data and then just copying and pasting them into one document and then loading that? Or
that's as simple as that for the morphological part, right? So for the syntax, there will be lots of subtle differences. We're not that far in unifying the syntactic annotation. So if you try to do something like that for syntax, you may get weird results. But for morphology, yes.
Great. Thank you. I'll try that out.
Okay, excellent. So we are almost over. I don't know if there are other questions. I don't know, Barbara, if you want to add something else. No? Okay.
Yeah, I can just say that following up, reinforcing what you were saying about getting more and more data, I think there is a lot of data that is sitting on people's desks on pieces of paper. So there's a lot of research being done with analysis that stays with the researchers. So getting more and more researchers to share and produce the data in standardized format is going to help hugely.
Yeah, sure. And then it's also, well, for a traditional scholar, maybe it looks, I can say, a boring work, a stupid work, but is not, because it's a difficult work. It's a very difficult work. For example, when you start rebanking, you understand that it's not easy at all. You have to know the grammar, you have to know the syntax, but it's also very interesting because you can see new things while doing this manual work, even if our goal, of course, is to get to use automatic methods, so to think in a new way, because this is another aspect. So to ask the computer new questions. So this is another important part of the methodology. Okay, I think so now is, well, our time is almost over. I don't know if there are no questions. I think we can finish. So thank you very much for this great session. Thank you both. So as you know, we have the class outline in GitHub, links to the tools, instructions, also a practical exercise, and Barbara and Doug are going to add also a link to the slides. So thank you very much. We will see you next week for another session about name entities extraction. So I'm sure we will talk again about these things, so collecting data, working with data, disambiguating data. So thank you very much, Barbara and Doug. And so see you next week for our next common session. Bye and good night.
Bye.